So you may have already seen models that are famous since the 60s, and I actually think that this particular model is very useful for power systems. It's called the hidden Markov model. So there is here a model that is already a graphical model, but essentially it says there is a dynamical model that I don't observe underlying everything, and my observation depend on this particular state of the world. But the idea here that we will understand better later when we describe statistical model is that these states evolve according to a simplified dependency. So they're not all dependent on the entire past, but this particular random state is only dependent on the previous past. And if you know the previous past, then everything becomes independent. And what you're trying is essentially to kind of eliminate uncertainty on the state, right? You want to know what's going on. And the reason why I say this is particularly important for sensing in the in power systems is that these are kind of the causes of what you observe, right? It could be an event, a contingency, and so on and so forth. Another one you may have seen is the famous Kalman filter, right? So this is used for prediction. So this is the counterpart of the Gaussian MMSE case that we looked at, except now the observations are not IID. They are evolving according to this type of stochastic process. So you have that the current observation is a function of the previous observation plus something that is completely IID and random, right? And so in this case, what you want to predict, your y is actually the future state. And you want to predict it from the current state. And the reason why you can't predict it, you always have this uncertainty which is added. You cannot do anything about that because it's completely independent from anything that you have observed. But if you are able to predict the initial state, then at least you can remove all the uncertainty on this, right? But you don't know what the initial state is, so you try to make progress. And the best progress that you can make in the mean-square error is what the Kalman filter tells you to do, which updates the covariance. This P is an update for the estimate for the current covariance of the error. These you can recognize the typical structure of the conditional mean that we saw before, and this is the covariance of your observation. You can recognize it has a similar structure. This is the matrix that you use in this mapping that you can see is sort of similar to the MMSE solution that we have, except it has a recursive structure. Okay? And this one is actually a good example for factor graphs that you are probably not going to explore further, but people that invented error correcting coding discovered graphical models independently. And so one popular way of correcting for errors is adding what are called parity bits. So you add some extra bits that are a Boolean sum of the bits that you want to transmit that are informative as checks, right? So if you know that the sum of some of the bits that you want to send has to give you 1 or 0, this is a Boolean 1 or 0, right? You can tell if there was an error, something has flipped, because they should match, and if they don't match, then you know that something has happened. Okay, so instead of just being upset that something has happened or just checking that something has happened, maybe you want to optimally decode, right? Optimally correct for these errors. And so here, this is what you have transmitted. This is what the channel does to you, is flipping errors with a certain probability on each of these bits. Typically, you assume that this flipping is uniform. And these are the conditions. This delta is 1 if this XOR gives you a 1, so it's nothing is different. Here, if nothing is different. And so these are telling you certain dependencies that exist between these bits that you added and the remaining part. So let's go back to the notion of conditional independence. Here you have L discretely jointly distributed random variable, and you know you can apply the chain rule, right? So let's say that you want to do a very simple operation, right? You want to start calculating the posterior, so one of the things that you want to do is to marginalize. Now, is this easy or is this difficult? It is in general quite difficult, right? Because even if these are discrete random variables, let's say that each of them has k values, this operation entails k to the L sums, right? So it's a pretty big object. And so this becomes easily impossible. It's not a formidable task. Now, this is not formidable if you have independent random variables, because in that case, it's trivial, actually. You already have all of the marginalized distribution as a product, and as you add up, these guys go to 1, so you get it. I mean, this is easy. So the general idea of associating a graph is precisely to understand if there is some way of using the chain rule that simplifies this part, right? So we said in conditional independence, if some of these are present here, then all of the other ones are irrelevant, okay? And that's exactly what an expression like this is trying to express. PA stands for the parents. They are those that affect, influence the children, right? And so this is simply a way of indicating a subset of the random variables that are here. So each of the xi is conditionally independent on the remaining random variables given the parents. And the language of Bayesian networks is very suggestive. It's always talking about family. I'm not sure why, but that's how it talks about things. So let's look at an example here. Here we have the x6 is conditionally independent on everything if you give me x4. x5 is conditionally independent of everything if you give me x3 and x4. So now this is a fairly kind of arbitrary structure, and all of these nodes have, sometimes they have only one parent, sometimes they have multiple parents. And so by definition, these are the definition of parents. Okay, so...
Excuse me, Anna. Yeah. Is there any rule to choose the PAs? Like how many PAs?
No, that's an intrinsic property of the distribution. So if you don't choose it correctly, you have to kind of see it, just like you see that a joint distribution factorizes. So you will see that this distribution has certain terms that you can split in products. And this is why I mentioned, for instance, in the Gaussian case, if you look at the inverse of the covariance, then you see it. You see you can split it. And so similarly for every other case, that's how you see it. So and then when you learn the distribution, you should learn to see how they split, right? So if you have to somehow utilize a combination of non-parametric and parametric modeling to understand how to guide your intuition about this. Okay, so why do we want to do this? Because when we do operations like marginalizing or maximizing, this actually gives us a recursive way of doing it that doesn't look at this k to the L different values. That's exactly what you do. So you kind of split it in a recursion. Okay, so what is a graph? A graph is a pair of sets. One is a set of nodes, V, and the other one is the set of edges, which is defined on the Cartesian product. So it takes pairs of vertices. And then it expresses a connection. So this is general definition of graph. And so we have that xi, xj is an edge. Here, these would be the random variables for our case of Bayesian network. And now these networks can be directed or indirected. So for instance, if you talk about parent-children direct relationship, that's a directed graph. But we will see that in another form of Bayesian networks, which are called Markov random fields, we utilize indirected relationship, right? And so the language of family actually kind of subsides. So there are a lot of definitions here, and I hope I don't bore you to death, but these are really the definitions that are critical to understand how these structures help you simplify and understand conditional independence and break this computation, right? Because it doesn't suffice just to know what are the parents. You can actually recursively calculate things because you know that you can look at isolated parts of this graph and then combine your calculations. So we define a path as a set of nodes that has essentially edges that allow you to move from one to the other. And these edges can be undirected or directed. You know, a path from x1 over x2 is in fact a directed path if there is at least one edge which is directed. Now, a cycle is just a path that closes on itself on the first node. And this is a definition which is quite useful. The definition of chain or trail is something that can go in one direction and vice versa, right? So this is called, this is what happens when you take even a set, a directed path, and you essentially replace all of them by undirected. Now, the type of Bayesian networks that we are going to encounter are always directed acyclic graphs. These random variables cannot have a dependence that loops around, okay? And so I'm going to call it DAG, I mean directed acyclic graph. And then we will call random variables parents or children depending on their position. So the parent has directed edges towards the children. And also we can define descendant and ancestors, which are relatives, generations before or after a relationship of parent and children. And then in particular, the worst case that we don't want to deal with is a complete graph. A complete graph brings you back to the chain rule, right? No matter how you organize your random variables, you are back to the chain rule, so you don't have any simplification. So you want essentially these graphs to be sparse, because then your factors depend on very few variables and you don't have all this explosion of your computations. So here, this is a problematic graph. You can see that there is a cycle. Here is that this is an acyclic graph because these are not in a cycle, right? Because they are directed towards here. So what is the Markov condition, right? So you may have heard of Markov processes, of Markov chains. Like this specifies a conditional independence in time, right? And then typically the way of expressing the Markov condition for a time series says the future depends only on the present, right? So if I have the present, I don't care about the past. So they just have a memory one step back. Unlike the IID process doesn't have any memory at all. So if you think about it, that's a conditional independent. Every parent is the present. Parent of the future is the present. So the graphical model, Bayesian graphical model, try to generalize this notion, right? Why? Because sometimes you may have multiple causes of something, right? So then you can say those are the parents of my observations, the random variables that I observe. And you can have a combination of the two. Those are called dynamic Bayesian networks, where you have some evolution of states, but then there are many possible things that can happen over time, and then you actually are expressing the dependencies. Another reason why this is very applicable is in diagnosis of diseases, right? Because oftentimes you have complicated relationship between the nutrition of the person, their genetics, and all of these aspects, right? And some things have nothing to do with each other, right? So they will be independent of each other, but they can contribute to the same symptom. So how do we express the shorthand for saying that this random variable is conditionally independent given the parents, right, from any other non-descendant, is this particular notation, okay? And so these are sort of called, the parents express some local independencies, but what you want is to understand, so the complexity of understanding these networks as well as the benefits come from understanding more complicated relationship. But this is essentially the connection. This theorem is the connection between graphs and Bayesian networks. So a certain graph is a Bayesian network structure if the joint distribution can be expressed as the product of the conditional distribution given the values of the parents. right? So it essentially encodes the simplified chain rule that you can utilize. So for instance, this graph over here, right, is a joint distribution of this, can be expressed as these factors, which you can easily understand. You see that 4 is the parent of 6, 5 has 2 parents, and then you have that 4 again has 2 parents, and instead x3 and x4 are only affected by x1. So you just can see that. And what is this? There's no edge at all. Independent, right? So if you have no edges, they are independent. So if you have graphs that are separate, that means those things have nothing to do with each other. But what you care mostly is conditional independence. So a consequence of the Markov condition is this product of conditional probabilities gives you the joint probabilities. And in addition, Markov condition is satisfied automatically if they encode this particular conditional independence. For probability mass functions, typically the graph and the distribution, the way the distribution breaks up is always consistent. But that's not true for every density. In any case, so if you start from a density, you can sort of build these graphs hierarchically, and then you essentially see the structure of the distribution, and you try to build it reasoning on the particular functions that you have. Okay, so here, again, you're not learning anything. You have the model. You're trying to inspect it. So basically now we can get to the notion of Bayesian network, now that we have understood this. A Bayesian network is nothing but a pair which has this graph that encodes the conditional independencies for a particular density. And the distribution for this case has to factorize over this DAG, right, this directed acyclic graph. Now, I want to just make a note of this. This is a big debate. Probability doesn't inform you about causality because Bayes is symmetric, right? But there are a lot of debates that some of these relationships are to be interpreted more as causality than others. And definitely we tend to interpret this way, in bioinformatics, the causes versus the symptoms. But that adds a level beyond what probabilities express. So we have to be careful in not confusing the two. Okay, so before we try to understand broader forms of independence, there is a particular thing that if you have certain observations, so you have a certain structure, and certain things are observed, right? So now that phenomenon is known to you. So basically, the phenomenon is better described through conditional probabilities. So the structure itself tells you a lot, obviously, about what random variables at that point are irrelevant, right? They are no longer at play, right? So if, as we said in the Markov process, I observe the present, then I don't care about the past. It means, at this point, if there was something in the past, everything I observe next doesn't tell me anything. Is not informative. So it actually, you will think that you are good in knowing the present, but you have lost something, right? Because you are not looking back.
Sorry. So I heard about this different orders Markov chains. Like sometimes you have single order or second order Markov chains.
Yes.
In that case, you are dependent.
Yeah, your dependency goes far away, multiple states. But in fact, you can always, as long as the memory is finite, you can always transform it in a multivariate process that has memory 1. So really, when you have anything that is in the perfect chain, the Markovian process is sufficient to handle it. Now let's look at this case. So there are two uninteresting connections here that you can find are recurrent in Bayesian networks, and one that is more interesting. So, and that is actually helpful to understand the influence of one random variable to the other. So here we want to understand how y influences the other variable. So if we know y, what happens? Okay? So they're called the serial or head-to-tail connection. This is the first one. The diverging or tail-to-tail connection. So this is parent has 2 children. and the converging, right? This is a child that has two parents. So here you can immediately understand this is kind of like the Markov process. If I know the present, then the past is irrelevant. So I basically only affect the future. In the diverging or tail-to-tail connection, if I know y, then everything stops. These two guys are conditionally independent. And so these could be like two symptoms, or this could be also the hidden Markov model type of things when I can observe two possible different random variables out of having a certain state, and that's what happens. This is a little bit more interesting because so here y is closing in both cases the evidence of the others, while in this case actually evidence on y is kind of opening information about these two. So these two originally don't have anything in common. They are totally independent. You cannot predict anything about z from the other. But if you now have two of these, either these two or these two, actually that tells you something about the other, right? So the other all of a sudden opens some so y opens some influence on the other. And so let me make a simple example. You have season a country, right? And then you see the weather is cloudy. So obviously the season doesn't tell you anything about what country it is, right? But if you see that it's summer and it's cloudy or rainy, then you probably are not in Arizona. So maybe you're in England, right? And obviously this is also true for the descendant. If you know it's summer and it rains, that's as good as knowing that it's cloudy. That's revealing information about the country. Okay, so that's why we say that it opens information or explains, and so that's actually an interesting connection. So converging connections are quite important, and they are key to understand how groups of nodes in a Bayesian graph are independent from other groups of nodes. And for this, we have to give yet another definition. So we call an active chain given a certain set of variables as follows. So let's say that we have a bunch of random variables in the set Z, and those are instantiated. We know what they are. And let's consider a certain chain, right? So these may have had directed links, but we made them all undirected. So that's a chain. Now, if originally some of these nodes were nodes where the edges converged, we say that this chain is active given this set because of these conversions, right? Because of these head-to-head connections that appears, and we have these things instantiated. So this opens information, this Z opens information about the variables in the chain. So it's active if in this converging connection, every variable in this convergent set are in Z, and there is no other node in the chain that is in Z. Okay, so only the point where actually originally the links are in Z. And that allows to introduce the notion of deseparation, which actually means something in terms of conditional independence of entire groups of random variables. So let's say that you have a subset X, a subset Y, and a subset Z, which is the one that you have observed. And these don't form a partition. They don't have any random variable in common, any node in common. So we say that these two sets, X and Y, are deseparated given Z if there is no active chain between the two. Okay? So there is nothing that is revealed by Z, right? It's not open. It's not an open connection. And the theorem shows that now this group of random variables given Z, that you can factorize it, right? So given Z, all the random variables in Y and the random variables in X are conditionally independent. Okay? So these, you see, you define the graph, you know the parents, the children are conditionally independent from the parents, but actually you can say much more by observing chains in the graph. Now there may be, these deseparations, it's definitely a sufficient condition, but you may not be able to identify all independencies through the deseparation. But it's a good indicator of how to split the statistics fairly easily once you know other statistics. So that's important to calculate conditional probabilities. So you can kind of split things that are uncertain for you, given a certain set of observations, fairly easily. Now again, more family-friendly notation. So we call a Markov blanket a set of nodes that comprise all the parents, all the children, and all the nodes that are sharing a child with this particular node. So we say that this is the blanket of a node. And the interesting thing is that once you have this blanket, if a node on the blanket is instantiated, so you have observed that, then the rest of the nodes that are part of the blanket are deseparated from the rest. Okay, so you can actually kind of take lumps of nodes that are neighbors and then observe immediately deseparation. Now, the notion of IMAPs is trying to sort of understand whether the graph encodes all possible relations, right, of conditional independence. And the reality is that you cannot claim that the graph itself can capture everything, but it can capture always a subset of them. And you say that the graph is faithful if it captures all of them. And typically for a probability mass function, you can actually always have a faithful representation. Its PDFs are a little nasty. And so sometimes you don't have. But it's pretty contrived example. So most graphical models, most are benign and faithful. So let's look at an example here of deseparation. So the red ones are the ones that we have revealed, right? So we want to understand what is deconnected and what is deseparated. So we can see that X5 is deconnected to X1 and X2. Why? Because, it seems that it shouldn't because these two are instantiated, but you see that there is X5, X6 here. So this information remains at play because this is not instantiated. So there are all other kind of considerations that you can say. You can say that this guy is blocked, like this is a parent of X3 and X4. So X1 is blocked by X3, but again, it kind of propagates because this is a connection that is a converging connection, so it's again opening up on this side. Here, this is kind of an obvious one, where now you know X7, so this is conditionally independent on everything else. And also you can see that here there is a Markov blanket, comprises X5, X3, X4, X7, and X8. Right? So this is the blanket. But not everything is instantiated in the blanket. Okay, so now everything here is known as a model in terms of statistics. How do you learn these statistics? You can utilize the type of parametric models that we were discussing before, right? So you can somehow guess that there is conditional independence, right? For instance, even in power systems, you may figure out that some observations can be informative with respect to some type of contingencies and not others. However, you need to most likely have a more detailed model of the probability law, and so this you may find a parametric or non-parametric approach. Typically is punishing to try to learn non-parametrically from frequency. This because you need a lot of data to do that. So let me give you some examples, some specific example of parametric models that are used. And some of them have become basically black box tools that people utilize without necessarily strongly reflecting on whether they're applicable or not. So one is the Sigmoidal Bayesian network that parameterizes. So this is here, all the variables are binary, so it can be either 0 or 1, right? So it could be success or insuccess, or the presence of a symptom given a cause, or stuff like this. So you have a certain set of parents. This is not important, but the way you the way you parameterize the parents is by saying that this has this kind of exponential denominator where the exponent is a linear combination of the random variables that are parents plus some constant, okay? So instead of applying the frequency approach and doing a histogram, now all you have to do is to learn these L parameters, and then you have a model. And so if you have at most k parents, then you have LK parameters to learn for every node, which may not be bad. But so again, you want a sparse graph. If this is not sparse, then you can kind of give up. So oftentimes, this is actually a particular neural network where you oftentimes, you model the interdependencies. These are hidden. There are some nodes in this network that are hidden, so you don't know these nodes, but you have some input nodes and some output nodes. So these could be a more complicated relationship where for instance, some of the factors, you have done some exams, but you haven't understood whether the tests that you made are really indicative of something. So there is something in the middle which is latent to you. And so that's a type of system where you may want to try to fit also a sigmoidal model for these hidden nodes and make a decision that you have a certain number of hidden nodes and how, wide is this layer. So this could be essentially what is utilized as, it's analogous to a neural network. The other example that we have to do is the linear Gaussian model. And as I said, in this case, is just graphical models are just a way of encoding recursively the calculation of posteriors. And also it gives you some way of thinking about the estimation. Instead of estimating the covariance, maybe you want to estimate the precision matrix, right? And that is indicative, in this case, exactly of the conditional independence. Another idea is, instead of utilizing densities, you could use the log of the density as an expression for your likelihood, right? And then the operations that you have to do, instead of multiplying probabilities, is doing sums of logarithms of probabilities, which for the Gaussian case is particularly appealing because these are simple quadratic functions. So it's very, calculating likelihood is equivalent to summing up all the exponents, basically. Another popular case is you don't have hidden nodes, you only have hidden causes, right? So there is no two layers, you don't have an input, you only have hidden causes, and these are the observations. And, it's quickly seen, and in case like this, unless you have sparsity here, this blows up the calculation of this. But this is a very frequent type of analysis. As I said, you don't know which contingency or which protective device went off, and you see symptoms, you're trying to figure out what is the likely cause given what you observe. And you can see that here, the more causes converge here, then the more this is sort of revealing things about this. So now let me go to undirected graphical models. So the problem with directed graphical models, we said that sometimes these maps are not faithful, and sometimes it is really difficult to have a single graph that encodes all of the conditional independence. The two things go hand in hand. So for instance, it actually is basically not possible to encode conditional independence between x1 and x4 given x2 and x3, and conditional independence between x2 and x3 given x1 and x4. You get two different graphs, and it's not possible to reconcile them. So this is why people came up with undirected graphs. And these are not called Bayesian networks. They are called Markov random fields. And Markov random fields are not directly utilizing conditional distributions to factorize the likelihood, but they are expressing indirectly a factorization of the likelihood. So all the nodes are unconnected. And what the composition does, it decomposes the likelihood in functions that are called potential functions or compatibility functions. These are all non-negative terms. And as we will see, basically gives a decomposition of the likelihood as a product of functions. So these are the potential functions I was mentioning. Now, since these are not probabilities, these are just positive functions, what this guy does is normalize correctly this product, okay? So you just have to integrate all these functions and you get Z. So we also call these kind of distributions Gibbs distribution. And a Gibbs distribution is just one that factorizes over a Markov random field. And so let's call the corresponding undirected graph H if each group of variables that is involved in k factors, so each group of variables, that is involved in k factors in the MRF essentially forms a complete subgraph, right? So there are certain vectors of variables that are here, and they form what we call a clique, right? A complete subgraph of the graph. And here in this example, you can see that there is this clique and there is this clique. And in particular, the maximal clique is a clique where we cannot include any other node and have a clique. So this is a maximal clique, right? Because this is a clique and this is a clique and this is a clique, but we can always add one of the other nodes and have a bigger clique. But we cannot add X4 and have a clique because these are not connected, right? So it's not fully connected. Okay, so what does it mean that we have a Gibbs factor with these variables? The set of these variables, though, is useless, right? Because these are not connected. And so also X3 and X4 will be in another Gibbs factor. So we have essentially, in this case, two Gibbs factors in the distribution. The equivalent of the notion of d-separation here, it's easier to understand because there are not these strange converging connections, but rather the notion of d-separations is really tied to the graph. You can actually see it. So the formal definition says that if you have a path, right, we don't have to distinguish between paths and chains, right, because these are undirected. We say that this is acting given Z if none of the variables in Z is in the path, right? And in fact, so this separation means essentially that so X and Y are d-separated given Z if essentially every path that starts from X and ends in Y has to go through Z, right? And so these are d-separated, right, because you have to go through Z. Here there is this way of not going through Z, right? So these are not d-separated. They are connected. And and we have an analogous theorem for this that says that I-maps so all the I-maps are just all these conditional independence conditions, right? And connections in the graph. They are the connections that you find in the MRF are a subset of what you can actually find in sorry. Okay, so and then this famous theorem that essentially proves that if you have an I-map, then you can certainly conclude that you can utilize those factors. You may break it more, but certainly no less. So let me give you only one example of MRF, which is the celebrated Ising model and some variations of this Ising model. So the Ising model, again, we are again in the realms of parameterizing these distributions so that we can estimate them. In the Ising model, these are also binary variables, and you are modeling directly the Gibbs factor taking an exponential where the exponent is a sum of terms, and the sum of terms are always pairs, products of random variables, and what you have to find to parameterize this likelihood in terms of Gibbs factor is these linear parameters, right? So again, you're trying to make the task of assigning these probabilities for this set of binary variables easy. The reason why you have J greater than Y, you don't want to duplicate another term with another coefficient because the product obviously is commutative. And generalization of these are the so-called Boltzmann machines, or the Potts model, where instead of having a linear term here, you have some arbitrary kernel, a function that you know, that has a structure that you know ahead of time. So how do we do computations on the MRF, right? So it seemed reasonable to do computation on the Bayesian network, right? Because we had encoded all of those conditional dependencies. But for MRF, what we do is we expand the graph in a specific way. And so in particular, whenever we have connections between nodes, right? So here there is a click here. So we know that there should be a Gibbs factor connected to this. We add another node here, a special node, which corresponds to the factor, right? So every time we have a factor, we have a particular node which goes by the label F, while these other guys go by the label X because they're random variables. And so here you have two examples. Here you could associate this, but you could also, have more factors, right? You could also have these factors if you want. And so in your model, you end up with these different graphs. So this is the one that we have in the figure. So now, what if you have a Bayesian network? Like, so imagine that these guys are directed. You could directly use, as instead of Gibbs factor, the conditional probabilities. But typically, what you do is you actually expand the graph. So if you have two converging nodes, right? So these are parents of the same child. What you do is you establish a connection. You put it in a clique. And this is called, again, moralization. It says you're trying to make a graph where all the parents of the same child are married, right? So that's the idea. Okay, let me go through this example, and this is going to be hopefully not a killer here. So the factor graphs are helpful because now we understand, if we look at the graph, we can see this is a tree. So trees means, this particular point at this particular node are kind of separating, right? You can take a root of this and start everything from the root, and that separates the different parts. So separation means that the factors are not connected, and so you can break things in those factors. So in particular, if we choose this particular node, then we are postulating that we can divide the likelihood. What this tree is telling us is that you can divide the likelihood in these three factors. Okay, these three Gibbs factors, where XA contains all of the variables that are in A, CH contains all of the variables that are in the second term, where there is XH over here, and CG contains all of the variables that are over here, right? So this is this factor, okay? So A is pretty big. These other guys are really tiny, right? Basically. Okay, so if I want to obtain the marginal, what do I have to do? I have to sum up all the Gibbs functions, and then I will have to normalize by adding these up. So this means that I can now break these summations. That's the main advantage, right? So because these terms don't depend on the same variable, so I can break it in these individual sums. And then the question is, how do I do this sum? I sort of recursively apply the idea. So how do I do this sum? The sum will contain all the factors that are in the graph. So if you look at this graph, then here we have a factor that includes this product. Then we have here a factor that includes these guys, a factor that includes this guy, right? So that's what we have here. Okay, so these are all the factors that were there, and then we have X3. So now I can, again, break these apart. I can just write it explicitly in the summation of these guys. I don't have to add with respect to X1 because that's what I'm interested as the variable, right? So I only have to saturate everything except X1. And here, that's the way numerically this is formulated. These particular calculations that I have in this summation, I break it up as certain summations that have to do with neighboring nodes. So here I have I want to saturate x6 and x5, okay? So x6 and x5, you see, are here. They are comprised in the same factor. And what I describe these is as a message between the factor here b to the node 2, the saturation of this function with respect to these two guys, right? So that's what I'm doing. I'm passing it on this. And if I pass it on this, then I have a function that depends only on x2. Similarly, if I look at x4, so here I can saturate, I can get a message out of these guys, and I can also get a message out of this factor. Okay, so these are just sums. I call it a message, but in fact it's just operating sum of the sums, and so on and so forth. So these are all the messages from the factor nodes to other nodes where they go to, right? And I'm trying to trickle down all these summations until I get everything except x1, which is the variable that I want to calculate the marginal of. I also have messages that go from the node to the factors, and what these messages are doing multiplications. And so what happens is that essentially what I am doing is these recursive operations. I send from factors to nodes sums, and then from nodes to factors products. And by doing that, I am essentially calculating all of this stuff, right? And it's kind of a formal way a machine can understand once I have encoded the graph to do it. So it's just an algorithm. It's a way of breaking up this in a systematic way once you have the graph. Okay? So therefore, we have two kinds of messages. One, they're called variable to factor messages, and these guys are always doing products, and the other ones are factor to variable messages, and these guys are doing sums of products weighted by the particular factor that is at the factor node. Okay? So if you have a tool for solving graphical models, you give it your factor graph, and it will generate essentially all the algorithm, the operation that you want. We want to marginalize this or marginalize that. So this is just illustrated here. You pass the messages from the factors to the node, you pass the messages from and then you pass the messages from the node to the factors. Okay? Okay, so this essentially calculates this factor. These other factors actually are fairly simple in the example that we gave, but you repeat this until you do everything that goes in the middle of the tree, which is the marginal that you wanted to compute. Right, so this essentially is done, and then you pass this factor to 1, and then you are essentially done. Right, so 1 is going to receive messages from here, messages from here, messages from here, and there you go. And now if you saturate with respect to x1, you get z, and you're done. Right, so you got it. Okay, so this is just the steps, the algorithm. Now what if you have some variables instantiated? Great. Then you don't have to sum over the variable, right? That's it. So if you have an observation and you want to marginalize the distribution given something, right? You are computing essentially the joint distribution in this case, right? And you do it that way. Now that is calculating the marginals, so marginalizing. The important algorithm to calculate the maximum a posteriori probability detection. In this case here we are dealing with masses of probability or estimation, wants to maximize instead of marginalizing. So in this case you have to actually do the algorithm in two passes. The first pass is to compute the maximum, and the second pass is to find where the maximum, what for particular instantiation of the variables you get the maximum, and that's your map estimate. And actually here, instead of doing sums, it's obvious how the sums will break if you don't have the same variables. The way to break the maximum is to notice that if you have a positive factor, and all these Gibbs factors are positive, right? That multiplies two numbers, b and c. You want to know which one is the greatest one between ab and ac. Since a is the same, you can pull out a and take the maximum of B and C. And so because of this, if you have the maximum of these three things, you can actually rewrite it as this thing. You are maximizing this times the maximum of that, and maximize, so basically the product of these three maxima, and then you have to take the maximum between these three. So that's the idea. And because of this idea, essentially what happens is that you do a procedure which is exactly analogous to what we were doing before, except instead of doing sums, you do maxima, and similarly you have the vector to factor that do the maxima, and the factor to vector that do products of these messages. Okay? And in the end, you find the maximum by doing this. But now you've found the maximum. You haven't found the point where it's maximum. So you have to have actually saved all these partial maxima that you calculated, because now you want to go backward and figure out. So here, the last variable where you took, like the last maximum that you took, you know what the variable was. But you don't remember what was the other ones. So you actually have to kind of backtrack and figure out what they are. And you do that by fixing the one that you know, right, already are the best one, and go backward. And sometimes it's better actually to do it taking the logarithm, because it's better to do sums than products sometimes, particularly if these are small numbers, you get into inaccuracies. So it's better to do this. So if you take the logarithms, then the initial message, instead of being 1, is 0, and then you keep going, and the last message, if you have a node which is a leaf, then you have just simply the factor with that particular node. Okay? So the reverse process is called backtracking.
Can I interrupt just for a second?
Yeah.
I just want to point out that max sum algorithm is also really useful if you're doing integer programming. If you have any integer programming problems that have network structure, max product and max sum, or the generalized distributive law family of algorithms, are really powerful and efficient ways of computing these things, and they're very closely related to dynamic programming algorithms. So
yeah, and I wonder if they discovered it, because
I think they all discovered it independently. And some very clever people pieced it all together.
I mean, because this is very narrowly focused on statistics, while that is kind of a
yeah, for sure. And sorry for interrupting you.
No, thank you. So I think I basically explained backtracking. You just go backward, like you know what the maximum is for x1, and you want to find now what other variables were giving you the maximum. So basically you go another flow backward, and you rediscover fixing those what you have. So I think I am blinking, so I will, so that's the example how you go back and you get x7 and x8. So I think I was on time, which is amazing, because there were a lot of slides. And the example was difficult. Okay, so we can actually block it now, and I will go to the last part after lunch.
Thank you.